This is 15.7 triple integrals in cylindrical coordinates. I think this will be fairly easy to grasp the general idea of. We saw an example at the end of the last lecture video that nicely kind of segued from the rectangular coordinate triple integrals to the cylindrical coordinates. And so I think this is going to feel pretty intuitive, but let's go through this by first introducing what are cylindrical coordinates. Let's formally introduce this. In plain language, cylindrical coordinates are polar coordinates representing positions in the xy plane, so taking the place of the xy variables, with the usual z coordinate attached on to extend it to 3 dimensions. So the polar coordinates tell you where you're at in the xy plane, then just let z be the usual value of z. It's your distance above that plane to get to your point. So I've laid out a little diagram of visually what we're thinking of. This blue and black point here can be expressed as xyz coordinates labeled in blue visually, or in r theta z coordinates labeled in black visually. Right? R is the distance from the z-axis out to your point, because if you projected that point back down to the xy plane, r would be the distance from the origin of the xy plane to that point. That by definition of polar coordinates. So r is the distance from this point to the z-axis. That's important, to the z-axis, not to the origin. That's different. Okay, and theta is the usual theta we have used all along. Theta in polar coordinates is measured from the positive x-axis upward towards the positive y-axis. And so with all these definitions, we just use what we know about polar and then just say also z is the same as it's always been, right? Because that's all that happened here. X and y, instead of describing your position in the horizontal plane, are in theta. We'll do that now. So we're going to write down these go-between formulas. They should look very familiar. These are just from polar coordinates. All those same relationships still hold. Right, so these should look fairly familiar to us. I want to start out here maybe by going through a pretty simple exercise of trying to plot some of these points. So let's scroll down here. Let's see what we can do here. Yeah, let's plot this point given in cylindrical coordinates and convert it to rectangular. This point is r equals 3, theta equals pi fourths, z equals 2. Pretty easy to plot. If you could draw a straight line, I suppose. Close enough. So here's our usual coordinate system. We know pi fourths tells us the angle from the positive x-axis measured towards the y-axis, all in the xy plane, that you need to go along to get to your point in the xy plane before going up 2 units in the z. And we know that this 3 tells us how far out from the z-axis to go. We go 3 units. And then once we get 3 units out at this pi fourths angle in the xy plane, we go up 2 units, because that's our z value. Right. So here we have it sketched out. This is our point. This is a nice way to draw it so you can very clearly see kind of visually where you're at in the plane. Draw this angle, the ray outward in the xy plane, then that little vertical segment upward there. Now if we want to convert this to rectangular, this is very easy because we have given formulas for this, right? Z equals z. Did I write that before? Yeah, we should specify. I said what x and y are up here. Z is just z. Z is what z's always been. Sorry about that. So we have these nice go-between formulas. We can just plug in r and theta into these and figure out what x, y, and z equal. X is 3 times cosine of pi fourths. y is 3 times sine of pi fourths. Z is 2. So it looks like we get, our point is 3 root 2 over 2, 3 root 2 over 2, 2. Great. So there we have it. We've plotted it very clearly in both coordinate systems, I think, and we have converted the point to rectangular. Oops. Just leave that. Okay. So let's go on to the next example where we go in the opposite direction. We find the cylindrical coordinates of given rectangular XYZ coordinates. This is not quite as easy, but I think we can handle it here. Maybe we just plot first to see what we're looking at. This is the point 5, 5, 10. 5, 5, 10 we'll say is up here. It doesn't have to be perfect looking. So where is our point? It looks like our point sits about here, right? So the ray that we're traveling along a distance r should be this ray from the origin out to this point, or from up here out to our actual point. That's going to be our r value. Theta is whatever angle this is. I think that's easy to see what theta is, right? We go out in the positive x direction, the same distance we go out in the positive y direction. That's got to be a pi fourths angle. There's just no other way that can be. All right. So we get a pi fourths angle here. You know, some of these might be a little more complicated. Maybe you have to use the fact that tangent of theta is y over x if you can't just look at the x value and the y value and guess the theta angle that produces that. Sometimes you do have to use this. Here I was able to just guess it. So theta is going to be pi over 4. We know r is just the hypotenuse of this little triangle down here that's 5 and 5 on the sides. So we can figure this out. Maybe you just think of this as being that one formula we already wrote down. Right, so 25 plus 25 is 50. Take a root. We do typically just insist that although you get a positive or negative root, that r is a distance outward from the origin. So in equations like this, we'll always take the positive root. But there are ways to consider a negative r, but we're not going to worry about that here. So here is r. Let's see. Let's go ahead and write it completely. Find cylindrical coordinates r theta z. Notice we didn't have to do anything for the z. We already know that. That's just 10 still. 5 pi fourths 10. There we have it. Okay. Let's take a look a little bit further down here about why we care about this coordinate system. And the big reason, I think, is that, and the reason that you do anything in multiple different ways in mathematics, is that sometimes one way is more convenient for the situation than other ways. So some situations, especially 3D triple integral situations, involve shapes that are very convenient in certain coordinate systems that are very and which are very inconvenient in others, like the XYZ system. So I want to see some standard graphs that are pretty nice and cylindrical that might be complicated in other systems. Turns out cylindrical is pretty good for graphs with symmetry about the z-axis. So let's see what we mean by that. For example, r equals a constant. What would that give us if we graphed it? Well, remember, r squared equals x squared plus y squared. So if r is k, r squared is k squared. We can see these give us circles of radius k centered at the origin. Right, so something that has a fairly complicated equation in x and y coordinates. Right, in x and y coordinates, remember the equation is x squared plus y squared equals k squared, or radius squared. It becomes very simple now in cylindrical coordinates. Sorry, in polar coordinates. That's what I've drawn here. But remember, we're in 3D and we didn't specify the z value in this equation, which means z can be anything. Our x and y values are trapped along this ring in the xy plane, but z can be any value. So when we transfer that to 3D, think of that circle, radius k, sitting down flat in the xy plane, and take any z value above or below that ring. It forms a circular cylinder. So I think this is a good way to see why we call this a cylindrical coordinate system. Something that's pretty complicated usually. A cylinder has a very nice, easy equation. R equals a constant. Right? So it's like a constant graph. That radius is k. Okay. So, circular cylinder. Notice that's something with symmetry around the z-axis. It's very nice in cylindrical coordinates. R equals 2 is a cylinder of radius 2, for example. Super simple equation, but pretty complicated graph. What about z equals r squared? We've kind of seen something like this before. Remember, if I replace r squared with what it equals in polar, x squared plus y squared, this is just a paraboloid. We're kind of seeing it in a simpler way, right? Seeing it that it's really just z equals the distance from the origin squared, or the distance from the z-axis squared. However far out from the z-axis you are, your z value is the square of that. So that gives us a paraboloid. We recognize that from the quadric surfaces. This equation from quadric surfaces. That should probably look smoother, but that's okay. Right. Easy little equation. It looks just like the equation of a parabola, but it's actually a 3D version of it, and we get that 3D nature for free without making the equation any more complicated, so long as we stick to cylindrical coordinates. What about z equals r? Well, again, we'll do the same little trick. If r squared equals x squared plus y squared, then r equals the square root of these things, and we get z equals r is just z equals the square root of x squared plus y squared. So square both sides, and you'll notice this equals x squared plus y squared. I thought I wrote it. There we go. Equals x squared plus y squared. Technically here, we're saying that r should be positive, and since we, no, let's just leave it alone. We said r could be positive or negative, so we won't specify that this root had to be positive or negative. Could be a negative value, I suppose. Sorry, this root. Could have been positive or negative. We allow negative r values, so we actually do get the full double cone. Right. Notice this thing is a 45-degree angle cone, the pi-fourths cone. If you change the coefficient on this r, it'll change the coefficient here, which will actually change the coefficients here and here. And so notice, for example, if I took like z equals root 3r, what would that give me? Well, let's just view it as we would in any given theta plane. So theta equals 0, for example. We're going to see the r is the distance away from the z-axis. So we could just plot this equation in this zr plane and see it's something that looks something like this. That's the z equals root 3r line there. It just means when we've gone up root 3, we've gone down, or we've gone over 1 unit to get a slope of 3 over 1. Well, maybe we can figure this out then. If we've got root 3 in height here, so root 3 on this side of this little triangle, 1 is the distance along this edge, then you can use Pythagorean theorem to find out this has to be 2. This is a special triangle. This is actually a 30, 60, 90 triangle. The angle here would be making it too small. Maybe I'll blow it up over here. The angle turns out to be a pi sixth here and a pi thirds here. Right, so you can take this picture apart using trig if you have a different coefficient than just a 1 like we saw in this original example. But you do get cones. Okay, so there's some nice shapes for us. Well, let's go on down here and talk about integration finally in this coordinate system. We saw some shapes that are going to be a mess in XYZ coordinates are pretty nice and cylindrical. So how do we use that to our advantage when integrating? Let's see. We're going to keep this very simple. We already know a general procedure for evaluating a function like this in XYZ coordinates. If you try to think of it as a double integral of a single integral. Right. Here I expressed it assuming that the dA is like a dx and y, so the x and y variables have taken the place of or what I've projected this into the xy plane to think of my footprint. And then I'm just integrating z from lower surface to upper surface over that footprint. So some surface up here, some surface down here. We get what's between them by integrating over their footprint. That's D. Here's upper surface. Here's lower surface. We integrate over the whole region by first covering all the x, y points in the footprint, then making sure z is integrated from lower surface to upper surface. It's all the points in between. So that's how we approached it before, but now, and as we've seen before, all we're going to do now is just express the double integral part in polar. That's exactly all we're going to do. We're going to rewrite this as, we'll say it's the double integral we're going to say theta goes from, I don't know, some theta 1 to theta 2, some starting to ending value. R goes from maybe some function of theta to some other function of theta. And then the z value goes from, really these surfaces, these are going to be in terms of x, y, and z. Well, let's do this a little better, sorry. I would just prefer to think of it this way probably. That's probably the nicest way to write this out. We just rewrite everything in the inner integral in cylindrical and rewrite the differential dA in polar. And these bounds, remember this is like my footprint D, in polar variables r and theta. Right? That's how we're going to break all these problems down. I don't think it's going to be too hard. You might wonder, well, I wouldn't say it's probably too unclear here. We're keeping the dz here. We're making the dA what it equals in polar because the dx and dy were changed to polar. I think it makes it clear that here in cylindrical, dv just equals all these differentials put together. r dz dr d theta. Right? So dv always equals this in cylindrical. We can kind of see that just from this way we picked it apart. So that's all we're going to have to do when we, let me make this note too. Here, lower surface. Here, upper surface. There we go. That's all we have to do. We think of it the same way, except we express that footprint in polar. That's exactly cylindrical coordinates. And as we saw in the last problem, it doesn't just have to be the x and y that can be replaced by r and theta. You could make the, I don't know, x and z be replaced by r and theta, and then you'd have a dy inside of here. Now you can choose any any pair of coordinates to play the role of the polar variables, and then just let the third one be its usual self. We did that in the last video. Maybe we'll get to one of those here. I'm not sure. So let's go a little bit further with an example to see how to use what we just described. Let's find the mass of the solid region E if its mass density at each point inside E is equal to the distance from the point to the z-axis times the height of the point above the xy plane. Now let's say E is the region inside x squared plus y squared equals 1, below z equals 3, and above the semisphere z equals root 4 minus x squared minus y squared. First thing I want to do, maybe take a second, ask yourself that question. It's the first thing you want to do. First thing I see here that we should do is draw a picture. If ever we can draw a picture in these problems, it will help us. We should always try to draw a picture. So I'm just going to start throwing pictures up here. See what we can do. X squared plus y squared equals 1. In the plane, that's a circle. But in 3D, that is a circular cylinder. Not perfect, doesn't have to be. Okay. And, I guess I don't need that dotted up there. And what is the radius of that? That is 1. Now, keep in mind there's an easier way to express this in cylindrical. This is r equals 1. Okay. We also want to stay below the z equals 3. So let's just say this height that I stopped my cylinder at, let's just say that was z equals 3 up there. So that's 3 units high. And so we want to stay below that. And we want to stay above the semisphere. This is a semisphere of radius 2, so it's actually stretching out further. It's maybe something like this. And it's going to intersect this thing Right, here's my semisphere. It's coming up. It looks a little oblong, but think of that as being a part of a sphere. There's the rest of it down below. And maybe that'll help. There we go. And we're saying E is the region that's above that. Oh no, I don't want to erase. E is the region below the z equals 3 plane, but above the semisphere. It's that stuff in there. So maybe we draw it over here on the side. Maybe we can see the idea here. It's a little piece of a cylinder with this little bump on the inside from the cylinder, or from the sphere coming up from below. So hopefully we can see roughly what we're talking about. That's E. Well, and keep in mind, we're finding the mass. In the last one, we didn't do an example of this, but we said the mass of a region is equal to the triple integral over the region of its mass density function times dV. Well, here we are given a description of the mass density, but we don't know it exactly. So let's write this down. Let's translate the wording here and figure out an expression for this. The mass density at each point in E is equal to the distance from the z-axis to the point. Well, if I have a point out in space, the distance to the z-axis by definition is r. Right? Remember that from above. Times the height above the xy plane, but that's just z. So there we go. We have, at least in cylindrical coordinates, we have an expression for this mass density function. It's r times z. So since we've got it in this form, let's express it, not rho of x, y, z, but r theta z. So that's what we need to integrate, rz dv. Well, let's see how we're actually going to set this up. Think of this little piece here. Notice this little circle I have drawn in my picture is already the footprint that this solid shape E would fall down into if we projected downward from above with light. Right? The shadow of that light would be this footprint here. That's like our region D that we want to integrate over. So we're going to express this triple integral over that region D that I've labeled, or express the triple integral as a double integral over D. And then inside of that, well, D is in the xy plane, so we still have z integration to take care of. Let's integrate rz dz, the z integration inside of that. And notice this should go from the lower bounding surface to the upper bounding surface in that footprint. So you can think of this as being your actual object. Inside of that footprint, the z values are starting at that semisphere and going up to the flat height of z equals 3. Semisphere up to 3. Semisphere up to 3. Semisphere up to the plane at 3. So we can say we need, certainly z is stopping at z equals 3, but it's starting at the semisphere. So let's write an equation of this semisphere. We already have it up here. Let's just write it in cylindrical coordinates. Right, factor out that negative, we see we have an x squared plus y squared inside, which is just r squared. So we're done with the z integration. Now all we have to do is finish up expressing this double integral on the outside. So let's finish that double integral. Kind of just leaving that there for now. We know dA in polar is r dr d theta. So now we're just looking at this footprint D and seeing what angles theta and what radii r away from the z-axis do we need to cover that whole footprint D up here. This footprint D. Well, theta should go from 0 to 2 pi because we're going all the way around that circle in the xy plane. right? We're not stopping or skipping any quadrants. R should go from 0, so we're at the origin in the xy plane, all the way out to 1, all the way out to the edge of that circle. And there we have it. We have our integral that will give us the mass. The mass is the integral of the density. That's what we've expressed here. Maybe we clean it up a little. Let's combine some stuff. That is our integral. Notice we could pull the r squared out of this first z integration. R looks like a constant as far as z is concerned. And notice all of this stuff inside the theta integration is independent of theta. So I could pull that theta integral out to the back, or think of slipping this out to the front of all the theta stuff. But I really have integral from 0 to 1, r squared, integral from the root up to 3, z dz. That integrated in r times the theta integral out back. And that theta integral is just 2 pi. I'll let you finish the rest. It's good practice. I think it's easy from here. Just standard integration. We'll save time in our video by leaving that to the viewer. Okay. So I'll say continue for fun. Okay. And everyone's like, what? Okay, let's go on. Okay. One more example, I think. See, did I have any other prepared? No, this is our last example. This will finish up our section. Let's sketch the region E whose volume is given by this strange triple integral given in rectangular. And then integrate, so the region of integration here is implied to be E. Then let's integrate x squared plus y squared over E with respect to V. So, to be clear, this is rectangular. It might look like it said vector there. Rectangular. So let's break this apart. This integral, we know that the outer two pieces, we can think of those as describing integration over some footprint or shadow of the actual 3D region. And since these outer integrals are in dy dx, we know we're thinking of that footprint as being in the xy plane. So let's start there. I'll leave this stuff inside so we can analyze it as well. But let's start there, right? And to be clear, this is just dv in rectangular, so triple integral of dv is volume. So this integral does represent the volume of this region E. So let's look at this. In the xy plane, we're saying the x variable goes from -2 to 2. Always want to start with the outer variable when decoding this way. Then the y variable goes from y equals negative this root to y equals positive this root. Y equals negative this root to y equals positive of that same root. Notice both, if I square them, give me this equation, which is just the circle of radius, the circle of radius 2. So it really looks like we're going from the negative half of the circle to the positive half of the circle with our y values. They're starting here on the negative root and going up to the positive root. This just says we're covering this whole disk of radius 2 centered at the origin. So that's our footprint, right? This is like our shadow region in the xy plane. It's this circle of radius 2. That's region D. And let's see, so it says that that's our whole region is contained above that, or below it potentially. But now we want to say the z values that we cover, for every x, y inside of this footprint here, the z values we cover start at this lower surface, z equals the square root of x squared plus y squared, and go up until they get to this other surface, the upper surface, z equals 2. Well, this is pretty easy to work out. This guy is just z equals r, which is a cone, right? 45-degree angle cone. And this guy is just the plane at z equals 2. It's just a flat surface at a height of 2 where we're stopping this thing. But notice when we get up to this height, z equals 2. When z equals 2, the cone has radius r equals 2. So right when we hit this top value where we're stopping, height of 2 there, our cone has a radius that's reached out to be also a radius of 2, just like our footprint indicates it should be. Right? So our footprint does make sense here. We're saying that our z values start on the cone and go up to this flat surface at a height of 2. Right? So we can picture this region now. It's just this cone. I guess that would be a little off. Let's do our perspective correctly here. This would be about here. Right. That is where we're capping this off here. That solid object, that's our region E. And so now we're being asked, now that we know what E is, now integrate x squared plus y squared over E. So let's see what we get. This is going to be easy and cylindrical. Let's see what we get. Triple integral over E of x squared plus y squared dv. I should write that, that's important. Well, we already know what the footprint looks like. It's that disk of radius 2 down in the xy plane. So this is going to be easy to break up as usual into a double integral of a single integral. And all we want to do is express the double integral in polar, right? That's cylindrical coordinates, and express everything on the inside integral in terms of those same coordinates. So to cover D in polar, or cylindrical really, we're just going to go from 0 to 2 pi with theta, right? Because we're going all the way around this circle. And we're going to go from 0 to 2, center of the circle, of the disk, out to the edge of the disk, at every one of those angles. Right? That's what our R values should do. So that covers the entire disk. You can throw your R in here now if you want. Now, inside of there, we just need to figure out, first expressing x squared plus y squared in cylindrical, that's easy. That's R squared. And dz stays as it is. Z didn't change, so its differential doesn't change. But this last integral, we need to carefully figure out. Right? Remember, on that z integral inside, we need the lower surface bounding z and the upper surface bounding z. So I look over here in this footprint, to stay in the region E, within this footprint, my values would have to start on the cone and go up to the flat surface z equals 2. So we're going to say z starts at the cone, but remember up here, we already said that cone has equation z equals r. So z equals r on the cone. It goes up till it hits just this flat height of 2. So z equals 2, where we stop. And this is our integral. Gather up that extra r with the r squared to make the r cubed. And there we have it. Now, the integration here is not too bad. Maybe I'll do a little step. Notice everything inside of here is, again, independent of theta. So I'm going to go ahead and pull the theta integration and just call that 2 pi. I'm pulling the r cubed out of the z integration because z sees the r cubed here as a constant. So it can come outside of that z integral. Not outside the r integral. It's stuck there. Let's see if we can finish this up quickly. dz integrated from 2 to r, from r to 2 is 2 minus r. I'll let you check that detail. I guess we might as well finish this. We've come this far. Let's go ahead and do it. Okay. What do we have? 2 pi out front. Let's go ahead and anti-differentiate. Looks like a half r to the 4th minus a 5th r to the 5th, evaluated from 0 to 2. Let's do this. A half of 2 to the 4th is 16, minus a 5th of 2 to the 5th is 32. And notice we get 0 at the bottom bound, so we're safe to just stop there. It looks like we're getting close. Not a very nice number. I get 36 pi over 5. Who knows? Seems believable. Okay. So that is it for this section. Next time we'll talk about yet another coordinate system, spherical coordinates.